Hello, it's Science Beam, and here we want to address how people might think that machine learning is something that can fix everything by making ML a little bit more concrete. So, first of all, let's not blame them. I'm pretty sure we all had our, shit, machine learning is gonna fix everything moment. Because, yeah, I know I did. Anyways, so in my last video, I talked about how I wanted to use machine learning for my internship with a biodegradable plastic. I set up the general aspects of how ML works, and that's all about relating properties we have control over and properties we want to maximize or minimize. So my specific example was with beads. So for example, we don't really want beads, we want to make fibers, we want long fibers. And there are specific voltage values or tip to collector distance values that make it more likely to get those defects, those beads. So we want to try to stay away from that. But some of you want specifics, such as exactly how ML adjusts to get those relationships we need to guide us when we conduct experiments. And this is what this video is about. So in the electrospinning paper, they use two methods, RSM and MLR. RSM isn't a machine learning method, but I think it's a good foundation to know what it does before we get into ML. RSM works by exploring relationships. So maybe our output is quadratic or cubic or quartic with respect to our input. You know, maybe monogamy isn't enough. Sometimes you gotta try polyamy? I don't know. RSM stands for Response Surface Methodology. What the fuck is that? So we plot our independent and dependent data points and end up with a surface. In our z-axis, our variable could be the number of beads we have. And we want to have as few as possible, right? Because there are many factors affecting this. The x and y axes are those factors. It's not just one, it's not just x and y, it's x, y, and z. So we can have 9 things affecting the number of beads, and most of the time in real life, that's what happens. There's more than just the x and y axes. There is x, y, a, b, c, d, e, f. Yeah, there's a lot. But what this just means is that there are multiple things affecting our result, our beads, our target. So a computer would try equations for all kinds of surfaces and see which one produces the most accurate one. Then the next question would be, how do you determine how accurate a surface is? So we take the difference between the surface predicted by our model from the actual surface, and we want this to be as small as possible. In other words, we're trying to get a simpler representation of all our data, right? And we're choosing the representation with values closest to the original set. Makes sense. It's like we're making clones because the clone is easier to deal with than the actual human being that is complex and unpredictable. But we don't have this blueprint of the human being. So what we try to do is kind of change every body part for this clone until we get one that is closest to that human being. So back to that surface thing. When we get that most accurate surface, which has its own equation, we then use this as a guide to get to that region that gives us the highest or lowest response, okay? We don't want beads at all. So we go to this region where the number of beads is at its minimum. So how do we determine this minimum region? It's not like the cases that we get a surface that you can easily see the minimum, right? So you have to pick a random spot and then look at the slope in 4 different directions, and you pick the slope where it's going down the most, because this is probably leading us to that minimum. As for ML, Machine Learning Regression, or MLR, often involves dividing our dataset into train and test groups. As straightforward as it sounds, the computer is training itself with part of the data you gave it, that train group. And yes, I will get more concrete with this in a little bit. Then they use the rest of our dataset to test whether or not their training was good enough. Plus, in ML, there's this thing called cross-validation, which divides our training group into even more groups. Let's say 4 out of 5 are used to make the model, right? And 1 is used for checking. Then they all kind of rotate until everyone was used as a checker. Okay, so let's get to the mechanism of how this would happen. So there were 3 kinds of machine learning methods they used here. We're still coming up with equations like in RSM, but with ML we use this thing called learning rate. So basically the difference between ML and RSM is that ML has these additional features like the train and test groups, the cross-validation, and now we have this thing called learning rate. So like in RSM, we start with a guess for our equation and then take the slope specifically. And this slope is also sometimes called the gradient. And this process of going to that minimum by checking the slope at different directions actually has a specific name. It's called gradient descent. So if you want to look into that further, there's the term for it. So far it's the same. So it is now at this point where things get a little spicy. We take an x value and subtract the learning rate multiplied by the slope at that point. What is the learning rate? It's basically a measure of how insane you are, to be honest. If you want to take big steps because you think it's going to get you to the smallest value for that new x, the quickest, you take that big learning rate. If you want to take it easy and you know you don't need to take those big ass steps to get there, you take a small learning rate. It's really just this value. And you see that if you take 2 big steps, you're not really getting to the target first, but instead you're parkouring around to values we don't really care about. But if you're taking 2 small steps, it's gonna take you a long time to get there. So we take this number and do the same thing. Subtract the rate multiplied by this new slope. And we keep going and going. How do you know when to stop? Remember, our function that we're basically running around is the difference between our predicted values and our actual values. So until we get to that minimum once again, we stop. We're good, because this minimum means that that difference is the smallest, so it's the most accurate. So one specific way to do all of this jumping around is through ridge regression, which uses this penalty coefficient called alpha. And this coefficient is something that avoids overfitting. So this is another specific term in ML. We want to get a general model, so if it's too specific to the data we had, that's what you call overfitting. And it won't be too helpful for future data. How does the penalty term help with that? Well, the specific equation looks like this. We're trying to minimize the difference between the guess value and actual value. It's still the same. But in addition to this, we also minimize the alpha multiplied by the slope. With this additional alpha term, we're giving the equation space to accommodate this issue. So in 5 minutes, I hope that is the plan, I was able to introduce RSM and this one other machine learning method called Ridge Regression. And for now, this should be enough to make machine learning more concrete instead of just seeing it as some quick fix to any problem that involves data. But if you want to compare other MLR methods, I have 2 more in the last part of this 3-part series, and I didn't put everything in one video because this way there's more focus on the setup, there's more focus on comparing RSM and MLR, and then there's another one where you get to be more focused on additional machine learning methods and you can focus on comparing them. Okay, there's a lot of focus. And well, the idea is to make everything more concrete, right? Instead of just bombarding you with information. So it's basically those 3 bullet points that I want to hit. So thank you so much for watching, and I hope to see you in the next video. Thanks for watching. What? I already said thank you. What the fuck?